Hello, my amazing Algebra 1/2 students. This is Mrs. A, and I love math. So today we're doing Saxon lesson number 9, and we're talking about points, lines, and rays. Oh my! You remember in a movie long ago called The Wizard of Oz, Dorothy said, "Lions and tigers and bears, oh my! Lions and tigers and bears, oh my!" So, points, lines, rays, oh my! Okay, so here is a point. No, not really. Maybe that. Or that, or that, or that. Oh no, none of those are points. A point is a concept. It's an idea of a location on or a spot. So a point is so small, it has no size at all. So if you kept on decreasing this size of this little dot until there was nothing there except a location or a spot, that would be a fairly good definition of a mathematical point. Okay, so we use a little dot to designate a point. So I may put a dot on a line and I may call it point A, but point A is really so small that we cannot see it. In fact, the line is so small we cannot see it. We just draw it because this is the definition of a curve. So we have these points that are like the building blocks of all of our mathematical figures. The points are the building blocks of the lines, and they're also the building blocks of the rays and everything else. But the points are so small you can't see them. So we think of the point as an idea of a location. You can't see it, but it's that spot, okay? So a curve, which I drew a curve here, is an endless connection of mathematical points. So if you connected a whole bunch of things that you cannot see into a curve, would you be able to see the curve? No. Okay, we draw a curve and we're drawing our best representation of that curve, but we can't really see that curve. It's just an idea of what is there. Okay, so a line would be a straight curve. So I would have to straighten that out and make it a straight line, and that would be the concept of a line. So because we cannot see these lines and points, we have to mathematically draw them with some thickness and a marker. But we all understand mathematically we cannot see that line in reality. It's a bunch of points that we can't see. Okay, so the next thing is how we represent these lines. Now, a line goes on and on forever. It's a connection of points that is straight that goes on and on forever. And so we designate which line we're talking about by calling the name of the points that are on the line. And notice that my line has arrows on both ends to represent that it goes on and on forever. And I can name this line using any two of the points that are on the line in any order that I want to. So I could say this line is AB, or I could say this line is BA, or I could say it is AM, or it's BM, or it's MB, or it's MA. I could think of a lot of them, okay? So that's how we name a line. And notice that this is called a little overbar, and the little overbar on the line has arrows just like the line that we're trying to represent has arrows. So what happens when we have a line segment? In other words, a piece of a line. So a piece of a line stops. So we could call a line segment AB, and that would be the point A and the point B, and there would be a line segment in between. So that's how we would note it. So when we're talking about a line segment, it's just an overbar with no arrows saying that it starts and it stops at A and B. Okay, now here we have a PQX, and notice that it is going on in one direction and starts. It does not have an arrow on this end. So it starts at P and it goes on through Q, through X, and it's everlasting. So it probably goes through some other points, but we only have these designated. So this is called a ray or a half line, and the ray has a start but not an end. When we're naming a ray, we will always start at its starting point. So we could call this ray PQ or PX, and the designation for a ray is one overbar with one arrow. Okay, my marker's dying here. So we have one overbar, and we're going to put since we're starting this ray at P, we're going to put the P first, and then we could put either one of these points, saying it goes through that point and continues. So we could just call this one PQ, or PX would have worked as well. So it has a start but no end. Okay, so now we're going to talk about a mathematical concept called an angle. And angles are intersections of two rays. So an angle has a vertex, which is the point of intersection. So if this were the angle that I were talking about, this place where the two rays intersect would be called the vertex. And this part here, usually this part in between the two rays, is called the angle. So we're designating the measure of that when we talk about how big an angle is. We're talking about how big is that opening in between those two rays. So if this opening here between the two rays is 90 degrees, then we call this one a right angle. Okay, a right angle has 90 degrees, and remember we use this little box here to designate 90 degrees, and so that would be a right angle. Now any angle that is fewer than 90 degrees is called acute. Okay, and I remember acute as being small, like, well, look at, there's a cute little baby. Okay, so we look at acute as a cute little baby. It's smaller than 90 degrees. Okay, so it's a baby angle. All right, and then we have angles that are larger than 90 degrees, and we call those obtuse. Okay, now I think of those as fat angles. Okay, because Mrs. A, I struggle with my weight a little bit, and a word for being a little bit overweight is obese. And obese and obtuse have the same front, the same prefix, ob. So ob means large. Okay, so a large angle is obtuse. Okay, and then we have what's called a straight angle. A straight angle is 180 degrees if that were that's the vertex there, but you never see any bend, okay, because the vertex, the two rays are actually lying on a straight line. So that would be a straight angle. And here in this next picture, we have that two right angles, if we put them side to side like that, would equal one straight angle. So 90 plus 90 is 180, and a straight angle is 180 degrees opening between the two rays, and a right angle is 90. So if we put two 90s right together, touching like that, then we would get together a a straight angle. So 2 rights make a straight.
Okay, here we have in 9C the concept of perimeter. Now, peri means around and metron means measure. And so perimeter means the distance around. So you had a little bit of Greek this morning. So here is a figure, which I've done my best to draw. It's in your book if you like that better. But notice that the figure is missing some pieces. I'm missing this piece. I'm missing this piece. I know what this one is, and I know the base here. I know this height is the same as this height over here. And then this is 4, and this is 2, and this is 6. But they did not give me this one and this one. So before I can add them all up to get the distance around, I need to figure out the 2 missing pieces. Okay, now, if this height is the same here, then wouldn't this drop down? And they do specify that all of the angles are right angles. So there's no angle tricks in this one. They're all right. And in my drawing, this one looks just a little higher than the other, so we could drop it down a little bit because my drawing is definitely not perfect. But we're saying that this is 8 and this is 8. So these are the same height here. And then wouldn't this one here have to be 6 as well? Because it's dropping down. Remember, they're all right angles. So this drop would have to be the same as it is on the other side. But how do we figure out this missing piece right here? So we know that the bottom piece is 14, and we know that all of the angles everywhere are right. Okay, so can we figure out this distance right here? What do you think? Think about what you would do in your head, and then I'm going to do this one for you. Okay, so wouldn't we take the base and subtract? We come in 4, and on the other side we come in 2. So 4 and 2 is 6. Wouldn't we have to take 14 and take away the 6 to get this distance here? So this distance here would be 8, because 8 plus 6 is 14. Now that we've figured that, can we add up all of the sides since we have all the sides represented? So when we add 8 plus 4 plus 6 plus 8 plus 6 plus 2 plus 8 plus 14, we get 56 feet. And that is in your book. They added them all up for you to get 56 feet. Okay, so let's come back with one more practice, and then I will set you loose on your homework. Okay, here is your practice problem. And notice we have a few missing items here. We know 4, we know 15, we're missing this one. We've got an 8, we've got a 14, we're missing the base. Okay, all of the angles are right. So let's reason this together. First of all, I want you to try to come up with them by yourself. So I want you to
pause your video.
Okay, so hopefully now you have the answers already written on there and have added them all up together. But I'm going to give you the answer now. 15 plus 8. Since this is a horizontal distance, it has no distance here because it's connecting to this one up here. 15 plus 8 is 23, so this distance down here must be 23. Okay, and then since this on this side is 14 and this is 4, doesn't this one have to be what's left between 4 and 14? It's got to climb up to 14 somehow, so this one right here needs to be 10. Okay, so now I've got to add all of these up together. So I'm going to do that over here. 23, and then 4, and then 15, and 10, and 8, and 14. Okay, I think I've got everything represented because I have 1, 2, 3, 4, 5, 6 sides 1, 2, 3, 4, 5, 6. So 3 plus 4 is 7, plus 5 is 12, plus 8 is 20, plus 4 is 24. Okay, 2 plus 2 is 4, 5, 6, 7. So 74 units of measure. Okay, they told us that those were in centimeters. So now we have 74 centimeters, and that was your practice problem.
And this is Mrs. A, and may God bless your day.